at the beginning, but I might go through reasonably quickly to remind you what it is. It's a land surface model comparison experiment. It followed on from the first preliminary experiment, which got published in 2015. In what I'm showing you here, we're just looking at latent, sensible, and carbon fluxes. We do have mental fluxes. We do have a few other things, radiation, but we're not looking at that. It's at 170 tower sites instead of 20 on the first experiment. We have a range of different models in the mechanistic model space, mostly land surface models, some ecosystem models, if I can call them that, some hydrology. But critically, we've got, I've lost my bracket of the end there, empirical models as well. And I'll try to explain to you why this is really important in a minute, but we're comparing our physically based models against out-of-sample empirical models. So they don't get to see the data at the site they're simulating at, they don't get to see the flux data from the site they're simulating at. And the kinds of questions we're trying to answer with this experiment are exactly how predictable are surface fluxes, how good are existing mechanistic models at making predictions of surface fluxes, and critically under which conditions or environments are they good, and which conditions or environments do we know that they can improve. And to remind you of the experiment setup, they're given vegetation type, reference height, canopy height, and meteorological forcing measured at these towers. So the idea is to not have a model that's calibrated. There is no calibration allowed. So we're not trying to test the ability of your model to fit the site. We're trying to get an understanding of what the fidelity of a model, given the right conditions, would be if it were doing a global simulation. So it's supposed to be a proxy for a global simulation, given all the right information. The empirical models are a huge part of this. Empirical models in sample, i.e. on the data they're trained at, you will never beat them because they are designed to fit data, right? But critically, when you look at them out of sample, they give you a low bound estimate of how much information there is in fluxes, about fluxes there is in the meteorology. And that, if you think about it, is a definition of predictability. It's at least a lower bound estimate of predictability. And that's key to the way the analysis is structured in this experiment. So we can use these empirical models to create physical performance model performance benchmarks, or I'm calling them mechanistic model performance benchmarks, by varying things like which variables do the empirical models have to make the predictions, which time and locations are they trained on, how complicated the empirical models, do we give them lagged variables or just instantaneous variables as a proxy for physical model states. And the idea here is that gives us a benchmark for the mechanistic models that can vary the expectations we have. If a site has really bad data, then the empirical model will do badly as well because the information's not there. If the site's really complex, it will do really badly as well. So this is the thing I added that I just wanted to make really clear to you. The blue line is a model, the black line are observations, and this is 4 seasons, a mean diurnal cycle, 4 seasons over many years at one particular flux site. That blue model is pretty close to the observations, and that you're looking at net ecosystem exchange of carbon there, okay? Now I'm going to show you the seasonal cycle of latent heat flux. This is the average monthly value over all the years of this particular site. The blue model, again, looks pretty good. It's pretty close to the black line, which is the observations. And the third one is, for the third flux we're looking at, this is a smooth time series of sensible heat flux. And again, that model looks really good, right? But my point to you is that model, that blue model, is an out-of-sample linear regression, instantaneous response to shortwave. Okay? So if you go to a meeting and you're shown plots like that and somebody says, that's really great model performance, it's not, because that's what you get if you just have an instantaneous response to shortwave. And this is out of sample. It hasn't seen this site data. It doesn't know this site. So my point is, if you're going to evaluate a model, you need some way to define how good it should be before you start. And looking at the qualitative, the sort of qualitative match of the two curves isn't really a good way to do that. Okay, and those are the 3 fluxes we're interested in, and that's what a linear response to shortwave looks like. So that's not a good model. That is a bad one. So now I'm going to go through a few results from Plummer 2, and what you're looking at here is just the mean sensible versus the mean late across all of the models. The grey dots in the background are individual sites. The center of the crosshairs there is where the OBS lies. I'm going to use the mouse to show people here. This line here is basically going through the OBS. It's a line of constant available energy, which is about 70 watts per meter squared. This is the line of constant Bowen ratio, where the OBS are. And you'll see that the observations are more spread around the Bowen ratio, so they differ mostly in their Bowen ratio, i.e. how they partition sensible latent heat, than they do in available energy, which is not that surprising, but it's saying that the differences between these models are in their partitioning, not in how much energy is available. And you'll see that the observations look a little bit lower than, in terms of available energy, than the models, and we all know that flux towers have an observation problem, and I'll show you in a second what happens if you use the energy balance corrected data, but to put a long story short, I don't think the energy balance correction is quite right. Okay, so the cable sits over here, it sits directly on top of CLM. JULES looks a little bit closer in this mean metric to the obs, that's kind of nice. The empirical models, surprisingly enough, sit bang on top of the observations, except for those two. Anyone want to guess why those two are there? Because that's exactly where the energy balance corrected data is, and those two are trained to fit the energy balance corrected data. Again, out of sample, so they haven't seen any of the sites that they're simulating here, but they know where that is. So that's what, if you do the energy balance correction, I don't know if you want to go backwards and forwards a little bit, but the energy balance corrected data is further away from the models than the raw data. That's just one little thing that made me go, oh, maybe that's not quite right. And there are, in the paper, I'll go into lots of detail, but I won't cover it here. I don't think the energy balance correction is quite right. It does good things for models. If your aim is to say energy balance correction will make our models look better, it really does for sensible heat, but not for latent. Okay, I don't have much to say about this plot. This is net system exchange versus latent heat, so you get, thanks. You get something like a, what do you efficiency out of this? That's where cable sits. The observations are under here. There's a black square under there. And the empirical models are there, except for the ones that have energy balance corrected latent heat, which is over there. And you can imagine that black square would shift over to be over here if it were energy balance corrected. I'm not going to show you that one. Other metrics that are going into this paper, this is error in energy evaporative fraction. So this is, if you think of latent plus sensible as the available energy, and I look at latent over latent plus sensible, this is saying what proportion of the available energy goes into latent heat flux, into evaporation or evapotranspiration, and this is the error in that. The box plot is over each site. So if box plot is above the line, you evaporate too much. If it's below the line, you evaporate too little. And the box plot's over each of the sites. So cable doesn't evaporate enough over all of these sites. JULES looks pretty good, centered where it should be centered. The empirical models are centered where they should be. If I go to energy balance corrected data, it doesn't change things a whole lot. So that's corrected, that's raw, that's corrected, that's raw. Okay. And remember, the empirical models here don't have anything to constrain their ratio of sensible to latent, but they managed to sit in the middle. Similar plot, but this time for water use efficiency, and I've expressed on the left vertical axis water use efficiency as micromoles of carbon absorbed per gram of water, even though a lot of this is evaporation, not actually transpiration. But that's the way I've set it up, and the pink lines and the axis on the right-hand side shows you that as a proportion of the size of the water use efficiency. And just to point out that cable is about 50% too little carbon. JULES isn't here because JULES didn't submit carbon. And the empirical models seem centered, more or less, some of them not, the really simple ones. So over here, this is one lim is there's just instantaneous response to shortwave, two lim is instantaneous response to shortwave and temperature, and then we go all the way up to more complicated empirical models like here and Random Forest. When I use the energy balance correction data, that changes a little bit, not a huge amount. But now you can see that the two energy balance corrected empirical approaches are again centered at 0 line. Okay, now this is kind of where it gets really interesting. And I just want to talk on this slide or the next few slides about what is different in Plumber 2 to Plumber 1 in the way that we try to use the empirical models to define how much potential improvement the models have. So in the original Plumber experiment, we looked at ranks. So if you imagine here, I've got, this is a range of metric values, okay? And let's think that we're looking at just mean bias. So the really great model in the original primary experiment would have been this 3K and 27 empirical models, cluster plus regression. It might have had a bias of 25 watts per meter squared. Cable might have had 35 watts per meter squared. A simpler empirical model 38, and another one much higher, so 63. Okay, so there's a range of metric values. In the original primary experiment, we mapped that onto ranks. So we just ranked the models. So cable would have gone to rank 2. And then we averaged the ranks over all of the possible metrics at all of the sites to try and get an aggregate measure of performance. And that gave us this horrendous plot that you might have remembered from that paper, which is really ugly, which just showed you the average rank over all the sites and metrics for sensible and latent heat. And I'm not going to go into looking at the detail on that plot, but just to remind you that that's how we got to that plot. In Plumber 2, the thing I did initially is taking that same, sorry, these are rearranged a little bit, but it's the same information. We took that range of metric values and I've mapped that onto just a 0 to 1 interval. So now that when models cluster together, they get values that are kind of the same, and try to put that together. This may seem technical, but you'll see why this matters. Okay, and that's what in the Plumber 2 paper I've called dependent normalized metric value. It's normalized because it's going between 0 and 1, and it's dependent because I've defined that 0 and 1 as the 0 to 1 range, the best performing and the worst performing. That includes the land model to define that range. And that's given us a new version of those Plumber plots. I'm not going to show you, I don't want to show you too much here because actually, and only last week, as a result of Matt Lipson's feedback, who's on the call, I've changed what the focus of this is. I was using this dependent normalized metric value as the basis of the analysis, and I've changed that now. And Matt made a really good suggestion, and that was this. Instead of that, I'm looking at independent normalized metric value, which is the same as what's there. I'm now scaling linearly between 0 and 1, but instead of doing that, I'm making 0 and 1 just defined by the reference benchmark. So for example, the linear model might be the worst, the worst up here, the complicated machine learning might be the best. If cable is better than that, it can go to a negative value. Okay, it can go outside the range. So now I'm allowing the 0 to 1 range to just be the reference empirical models, and cable can go and be better than that. So we get a value like minus 0.19, or it could be worse than that. If it had a bias of say 101 watts per meter squared, it'd be up at 2. Okay, and then the picture gets really different when you allow that. Okay, so necessarily each panel on this plot has a different vertical axis. Yeah, last slide. Okay, so each panel on this plot has a different vertical axis. Because of the way the normalized metric range is described here, the 3 reference models, that's the linear regression against shortwave all the way through the LSTM, the red, yellow, and green, are actually the same in every plot. I mean, the plots are maybe slightly different because there's latent, sensible, and carbon-magnetic system exchange, and some models only have 1 of these, some models only have 2. But the point is that the value for latent heat and sensible heat and magnetic system exchange in the 3 reference models is the same in every panel, and it's only because the vertical axis is different. But what you can see is that the mechanistic model, which is, for example, is JULES GL9, is the blue line. This is not serious. The Japanese model is the blue line. The blue line is always the model that's in the title of the plot. Okay. And the horrible thing here is that if you average over all of the metrics, no single model does better than the linear regression against shortwave. And that's a little bit of a shock. This is with the raw data. And if you go to the energy balance corrected data, it's a little bit better. Over all variables, 2 models do better than the linear regression against shortwave. Any guesses as to which models they are? Okay. CLM and cable. So cable, even before all this stuff came up as the best model for carbon. I don't know if you can see, but the only models in this raw flux data plot that ever do better than the linear model are the really established land surface models. The ecosystem models don't come close. The really established land surface models, which I assume have had multiple constraints and been developed over a long time, tend to do better than the linear model. There you go, cable does better for carbon and latent heat flux, this cable pop. One of the CH Tesla ones does better for latent heat flux. That's been around for a while. CLM does better for latent heat flux, didn't submit carbon. JULES didn't submit carbon, just does better for latent heat flux there. And then you have to go all the way to Orchidea is the last one. That gets better than the new model. But averaged over all of the variables with the raw data, and I still think the raw data might be more useful than the energy balance corrected data, but I'm not talking about that today in the paper. I'm trying to outline why. None of them do better than the new model. And that is a bit of a problem, I think. But it gives us a really nice target, and we have really useful flux tower data that can tell us that. And it's one of the few places, I know we're running global models, it's one of the very few places we have enough data that is close enough to observe to actually constrain a model to say when a model is not doing well. And that is pretty unusual. We can't do that at the global scale, in my opinion. We can do that at flux towers. So we can actually evaluate processes at flux towers. That's a plus.
Okay, thank you, Gab. We have a few minutes for questions or comments.
Thanks, Gab. That was very nice. Quick question, two quick questions really. How is the energy balance closure correction applied? Sorry, everyone.
It's a complicated one. It's what was applied for FluxNet 2015. We replicated that for the OzFlux and the Latwil sites that were not in, did not have energy balance corrected data, but the nature of the correction varies on the diurnal cycles depending on the conditions. It's a very complicated thing. I pointed out these results and a few of the reasons why I don't think it's right to Dario, and he said, yes, we know it's not right. So I don't know whether they've got anything better, but I assume if there's going to be an ongoing process in one flux rather than a bulk release like FluxNet 2015, they will apply whatever they think would be better.
So the second question then was, is the same correction then, which effectively increases the energy fluxes, is the same correction applied to the carbon fluxes?
No.
Why not?
I don't know. That's not something they did. I'm not entirely sure how you'd want to do that. You would have to then partition transpiration and evaporation to work out what proportion of it you want to apply something.
It's just that the reduction in carbon fluxes seems to follow the same pattern as the reduction in energy fluxes.
Yeah.
For the same reasons, actually.
The other thing that I didn't point out is you can see that all of the models do comfortably worse on sensible heat relative to what information is available. And you would think that's the simplest of the fluxes to predict. So I would, I don't know. There's no water involved really. I mean, there is a little bit, but I would think that's the low-hanging fruit thing to do, is to try a few crude things there to see what would give us a better approach.
Just that comment on sensible heat flux. That's a very interesting one, and I saw Ian shaking his head that sensible heat flux is the easiest. I guess it started me thinking sensible heat flux probably has less other multiple constraints. LE, you have energy and carbon to constrain it. H, I'm just thinking of this as a speak. Anyway, it is interesting that H does this. Reminds me of small things. Others more insight. Can I just say, I think this is really interesting, and I'd hazard a guess that the flux community in Australia might be pretty keen to
They should
have a conversation about this as well. Yeah. So yeah, really nice. Thanks, Kat.
So my follow-up question on that, Alan's picked up my main reason why I think sensible heat flux is the hard one. I actually think that none of our land surface models actually have the right inputs to get the sensible heat flux correct. You need to have boundary layer height in there, because it dependent on what the boundary layer height is and what the structure above the boundary layer is you will end up with getting different low frequency contribution to a sensible heat flux. If we don't have the boundary layer height, our ancestors models are going to be limited at some point.
I can give a retort to that, while it may, I'm not going to disagree with you that it's really important. Keep in mind that machine learning doesn't have access to that. And the linear regression doesn't have access to that. And it can do it like that.
So Ian's comment about boundary layer height, and the other thing I was wondering about, and again, I'm just putting ideas out there, is how good is our momentum flux U star? Because I think H is going to be linked to that as well. There's probably a connection between these things.
I would read this much more as there is something that we have got wrong that is hobbling the models rather than we need another thing in there. Yeah, so that apologies, but that we have the information to do momentum flux. I haven't done the analysis yet. It won't be the first paper. It's coming.
We've had very few comments, questions online, but I do see that there's some stuff in the chat from the session. So
You guys got
Hey, I've got a question if that's all right.
Go ahead, Dan.
Thanks, Gab. Fascinating talk. And great that cable's performing so well. Are there parts of the model that you know are leading to that high or good performance, and parts which you think are holding it back?
I reckon you could have a guess and we could all argue about it for a while, but no.
I think one of the key things about your talk, you've got too small a sample size to really be definitive, but the models that are performing well come from groups that attack the land modeling systematically. They have infrastructure, they have scale, they have collaboration, they have evaluation, etc., etc., etc. So that noting that those better models are supported by integrated groups, I think it's really important. It reminds us that land-surface models don't emerge from some awesome champion, they emerge from groups confronted over many years by data and capabilities. Something to think about moving forward. It comes back to the previous couple of talks on evaluation suites. The sooner we have those evaluation suites bedded in, and we're not allowed to do anything until we've gone through those evaluation suites systematically, the better.
Okay, so the other thing to point out is that it's about 3 or 4 days work to make sure all of the metrics you've seen here are part of EdgeCAD. So it's not very much at all. It's in the same, it's been written in the same system to run on MEO. So I think there's a huge opportunity here that we have the evaluation that can point out these problems, and when we might have resolved these problems that other groups may not be as aware of. So if we get our automated system up and we can actually use this, we could jump ahead of the game quite quickly. And I don't suspect it's a very difficult thing to find, but there's an opportunity, I reckon.